This is Jayanti. Today I am here to discuss about the parameters of the transmission line. Actually, the transmission line is the main part of the power system among the three parts. The transmission line has to supply the power from the generating station to different load center via distribution system. And side by side, it also transmission line also caters the emergency services by interconnecting the neighboring load region or neighboring distribution system also. The transmission lines are overhead transmission lines are consisting of number of conductors connected in parallel, and each of the parallel conductors are insulated from each other, and side by side each conductor itself is insulated from earth also. The overhead transmission line are having four electrical parameters. That one is resistance, then inductance, capacitance, and the last one is the shunt conductance. The resistance. This resistance is very important parameter because and if the resistance will increase for transmission line, then the line loss will also be increased, and thereby it affects the transmission efficiency as well as the cost of the transmission. Next one is the inductance. Actually, the transmission capacity, power or power transmission capacity through the transmission line is controlled by this inductance of the transmission line. Next one is the capacitance. The capacitance is it requires huge line charging current, and especially for medium and long transmission line, this line charging current is huge. Under the no load condition, on the light load condition, the capacitance will draw due to the existence of the capacitance. The line charging current will be huge, and for this reason, the receiving end voltage will be greater than sending end voltage, and that phenomenon is called the Ferranti effect. And for short transmission line, the effect of capacitance can be ignored. Next one is the shunt conductance. The shunt conductance mainly arises in case of the transmission line due to the leakage current flowing through or flowing across the insulator. But as the leakage current is very small compared to the main current flowing through the transmission line, that's why the leakage current can be ignored, and thereby the shunt conductance can be ignored there. These are the four parameters of resistance, that is resistance, inductance, capacitance, and the shunt conductance. Let's consider first one, the resistance of the transmission line. So before going to the resistance of the transmission line, all of us know that there are two types of supply. One is the DC supply and another one is the AC supply. So depending upon the supply, the resistance can be also classified as, first one is the DC resistance, another one is the AC resistance. And obviously, while we are considering DC or AC resistance, the frequency is automatically will be under consideration. So resistance is the function of, first one is the frequency, then next one is the spiraling, and then third one is the temperature. Now, for the DC resistance, of a solid ground conductor, the expression can be written as RDC equals to rho into L by A. This is very common expression, where rho is the resistivity of the conductor, L is the length of the conductor, and A is the cross-sectional area of the conductor. If the conductor can be taken as the cylindrical in nature and supposed to say the length of the conductor we are assuming here as L unit, and if the cross-sectional area is taken as A centimeter square or meter square, if L is in centimeter, A is in centimeter square, then, and if rho is the resistivity, then the RDC, that is the DC resistance of the solid ground conductor, can be written as RDC equals to rho into L by A. Next one, if we are considering the stranded conductor, then what is happening here? Due to the spiraling, the length of the conductor itself will be increased. That means here L will be increased and thereby the resistance of the DC conductor will be increased. So in this case, for the spiraling operation, DC resistance of the stranded conductor will be greater compared to the value obtained by this expression. Next one, RDC less than RAC, because the current, if the AC supply is applied across the conductor, then the conductor itself has the tendency to flow through the surface of the conductor, to flow through the surface of the conductor or near the surface of the conductor. And if we will proceed or go, if we will go towards the center of the conductor or central axis of the conductor, then the current will flow through the central axis of the conductor will be zero. And this effect is called the skin effect. This effect is called the skin effect. That means the current has a tendency to pass through the surface of the conductor or near the surface of the conductor. So here the current distribution is not uniform. And if the frequency, that means here the cross-sectional area A, cross-sectional area A is decreased here, thereby RDC, thereby not RDC, RAC will be increased. Now if frequency is increasing, then RAC will be increasing in nature, because here the cross-sectional area, effective cross-sectional area, not actual cross-sectional area, effective cross-sectional area will be decreased. Effective cross-sectional area means through which the current is flowing through the conductor. Effective cross-sectional area is decreasing with the increase in frequency, and thereby RAC will be increased. And obvious from this expression, RDC is less than RAC or RAC is greater than RDC. Next one is the temperature. Effect of temperature on the resistance. We know that the thumb rule, that one is also very popular expression. RT equals to R0 into 1 plus alpha 0 into T, where R0 is the resistance of the conductor at 0 degrees centigrade, kiloohm of course. RT is the resistance kiloohm at T degrees centigrade. Alpha 0 is the temperature coefficient of resistance at 0 degrees centigrade. Now among these in this expression, among RT and R0, if any one of these expression is known to us, then we can easily find out the another. Suppose to say there are two temperatures, two different temperatures. One is T1 degree centigrade, another one is T2 degree centigrade. Then if R0 is known to us, alpha 0 is known to us, then we can write this expression as R1 equals to R0 into 1 plus alpha 0 into T1, just by applying this expression. Now RT equals to R0 into 1 plus alpha 0 into T. And easily we can find out among this expression, if RT is known to us, then we can easily find out R1. Next, let's consider the inductance of transmission line. So, before going to inductance of the transmission line, we know that before going to the inductance of the transmission line, we know that if the voltage, if a current carrying conductor, for a current carrying conductor, a magnetic field will be produced across the conductor. If there is a current carrying conductor, suppose to say I current is flowing through it, then a magnetic field will be produced surrounding the conductor, and the magnetic field lines of force will be in a plane perpendicular to the plane of the conductor, and of course an EMF will be induced across this conductor. EMF will be induced across this conductor. The expression for this EMF will be E equals to d psi dt. E equals to d psi dt, where d psi dt, d psi is nothing but the flux linkage. Psi is nothing but the flux linkage of the conductor due to current flowing through this conductor. And this expression again can be written as d side di into di dt, and d side di again can be written as L. The L is nothing but the inductor. L is nothing but the inductor. We can write this expression voltage induced in a conductor E equals to L into di dt just by following the Faraday's law. Now, supposed to say for a linear magnetic circuit, the rate of change of flux with respect to the change in current is constant. Then we can write this expression as phi by I. L equals to phi by I. And again, this expression can be written as phi equals to L into I. The flux linkage psi equals to L into I. For AC, this expression can be written as lambda equals to L into I. Just this expression is rewritten as lambda equals to L into I, while we will supply the AC across the conductor or through the conductor. AC current will flow. And here, lambda and I are the RMS value of the flux linkage and current. Lambda and I are the RMS value of the flux linkage and current. Lambda is the RMS value of flux linkage and I is the RMS value of current. Next, by Ampere's second law, we also know this expression, that is closed line integral of magnetic field intensity equals to I enclosed. I enclosed means current enclosed by the Amperian path, current enclosed by the Amperian path, and we are coming soon to this expression in detail. Next one is the relation between P and A, that is the magnetic field density. P is nothing but the magnetic field density, and H is nothing but the field intensity. Magnetic field intensity, where mu is the permeability, and it's nothing but the product of mu naught and mu r, where mu naught equals to permeability of the free space, and is having the value 4 pi into 10 to the power minus 7 Henry per meter. Next one is the mu r, that is the relative permeability. Mu r, that is relative permeability. And for steady state AC voltage drop due to alternating flux linkage, again this expression can be written as E equals to L into di dt. Here d dt can be substituted by j omega. So we can write this expression as j omega into L into I. J omega into L into I, that one equal to j omega into lambda. E equals to j omega into lambda. Now, mutual inductance between two circuits. This L was the self-inductance. Now let's come to the concept of mutual inductance between two circuits. Suppose to say there are two conductors carrying current, and the distance between them is not much more, such that suppose to say this one conductor 1 is carrying current I1 and conductor 2 is carrying current I2, and of course one flux will be produced here. Here also the flux will be produced. Another flux linking with both the conductors will be produced there. That is the mutual flux linkage with both the conductors. Okay, now Due to the mutual effect, another inductance will be produced here, that is called the mutual inductance. Due to the mutual effect or flux linking with both the conductors, another inductance is produced here, that is M12. Again, it can be written as M21. And the self-inductance for conductor 1 is L1. Here for conductor 2 it is L2. So this equation can be written as M21 equals to lambda 21 divided by I1. M21 equals to lambda 21 divided by I1. That means the mutual inductance of this conductor 2 is nothing but the flux linkage due to the with the current flowing through this conductor flux produced for the conductor 2 linking with the current I1. That's why we can write this expression as M21 equals to lambda 21 divided by I1. So the voltage drop in circuit 2 due to current in circuit 1. Voltage drop in circuit 2 due to current in circuit 1 can be written as, just by substituting this expression, it is equals to j omega. Instead of A, we have to write here M21, that is mutual inductance, into I1. Voltage drop in the circuit 2 due to current in circuit 1. It can be written as E2 equals to j omega M21 into I1 equals to j omega into lambda to 1. J omega into lambda to 1. So this one is the brief about the entire discussion of today's session. That is actually the supply. We have today we discuss about the single phase supply inductance of single phase transmission line, mainly the inductance of single phase transmission line. Before going to this concept, we must have the knowledge about the inductance of single conductor. So for the single conductor consideration, we have to consider both the internal inductance as well as the inductance due to external flux linkage. And thereby the inductance of single conductor will be calculated, and thereafter the inductance of single phase 2 wire line will be considered. Inductance of single phase 2 wire line considered, and this one will be self, and after that self and mutual inductances. Will be separated. Or we are coming from this expression, inductance of single phase 2 wire lines will be generalized to the expression having both the self and mutual inductances. So first one is the inductance of a single conductor. We know that transmission lines are composed of number of parallel conductors, and we are assuming here the conductor is having the infinite length. And for the inductance of single conductor, we will assume here the return path is assumed far away from the incoming conductor or the conductor under consideration. That's why the return path or return conductor will not affect the fluxes or will not link with the current flowing through the conductor, or there will be no mutual effect. Here both the flux inside the conductor and the external flux are considered. Now, I am showing the conductor here. Let's consider the cross-sectional view of the conductor. Carrying current supposed to say I plus I. We are considering only one conductor. The return path is far away from this conductor. And supposed to say here the radius of the conductor is R. Just see here there are the internal fluxes. So internal flux progressively links a smaller amount of current as proceed inwards or towards the center of the conductor due to the skin effect. Because the less amount of current will flow through the center of the conductor, and a large amount of current will flow through the surface of the conductor. Next, external flux. If we consider here the external flux that links total current out inside the conductor, this total current means I current will be confined by the external flux consideration. So let's consider first one is the internal inductance. So before going to the consideration of internal inductance, we have to draw the Amperian path inside the conductor, and considering the same center of the conductor, supposed to say having the radius x here, and we have to find out first of all here the magnetic field intensity. We have to find out here the magnetic field intensity at this point. Now we know that here the direction of magnetic field intensity will be in the tangential direction at this point. Okay. Now by Ampere's circular law, this one is the curve or the curve shown by the dotted line is nothing but the Amperian path here. And by Ampere's circular law, we know that the closed line integral of Hx, closed line integral of Hx will be nothing but Ix. By Ix is the current enclosed up to the region having the radius x. Here Ix is nothing but the current enclosed by this Amperian path or the closed path. Now we are assuming here symmetrical field. We are assuming here symmetrical field, that is Hx is constant at the point distant at any point distant x from the center of the conductor. Then we can write by integrating this equation, we can write 2 pi x into Hx equals to Ix. Now suppose to say we are considering here the skin effect is ignored or neglected. Skin effect can be neglected. Assuming that means we are assuming uniform current density. So we can write here Ix divided by pi x square equals to I divided by pi r square. Assuming the uniform current density, neglected skin effect, I equals to Ix divided by pi x square equals to I divided by pi r square, and ultimately Ix equals to s square by r square into I. Thereby the field intensity can be given as, just by substituting this Ix here, Hx equals to Ix divided by 2 pi x here. So ultimately it will be I into x divided by 2 pi r square. I into x divided by 2 pi r square. For non-magnetic conductor with constant permeability, the relationship between magnetic field intensity and the flux density can be written as Vx equals to mu naught into Hx. Vx equals to mu naught into Hx. Put here Hx, mu naught into I into x divided by 2 pi r square. And we are considering here for a small region. We are considering a small region of thickness Bx, supposed to say. We are considering here a small region having the thickness Ex and the length of the conductor 1 meter. The flux can be written as d phi x equals to Bx into 1. Just by multiplying the area with Bx, that is the flux density up to x, that can be written as mu naught into I into x divided by 2 pi r square into dx. And due to flux linkage with fractional turn of the total current, fractional term means x square by r square into I. d lambda x, that is the flux linkage, can be written as x square by r square into d phi x, which ultimately gives us mu naught I divided by 2 pi r to the power 4 into x cube into dx. So the total internal flux linkage can be obtained just by integrating this d lambda x from 0 to radius r, Now the total flux linkage, internal flux linkage can be obtained just by taking integration of this term that one equals to d lambda x from 0 to r. I am showing it directly 0 to r mu naught I divided by 2 pi r to the power 4 x cube dx. That one is to mu naught I divided by 2 pi r to the power 4 into r to the power 4 by 4. Not r to the power 4, actually it will be x to the power 4 by 4. Then it will become 0 to r equals to mu naught I r to the power 4 divided by 8 pi r to the power 4. In numerator and denominator, r to the power 4 are cancelling each other. Now by putting the value of mu naught here, that is 4 pi into 10 to the power minus 7 I divided by 8 pi. That will give us 0.5 into 10 to the minus 7 I. 0.5 into 10 to the power minus 7 I. And from the generalized expression of inductance, self-inductance, L internal equals to lambda internal by I, that is 0.5 into 10 to the power minus 7. Obviously, unit is Henry. Next one is inductance due to external flux linkage. Already we have covered the inductance due to internal flux linkage. Next one is we are considering here inductance due to external flux linkage. Same as before, we are considering here the conductor having radius r and carrying current I. We are considering here the cross-sectional view, and we are considering here the 2 points. We are considering here the 2 points P and Q, and distance, supposed to say at distance D1 P and Q. At distance D1, another one is D2. So we have to find out the inductance due to the external flux linkages in between the point P and Q. And we know that the field intensity is given by Hs equals to I divided by 2 pi h. So to find out the flux linkage of conductor due to fluxes between P and Q, we have to again consider the Amperian path in between the points P and Q, having the radius in between D1 and D2. Supposed to say this one is at a distance x from the center of the conductor, that is center is denoted by O here. And same as before, the field intensity will be at tangential direction at this point. Okay, and the field intensity is given by Hs equals to I divided by 2 pi h. So this one is the difference in between the inductance due to the internal flux linkage and the external flux linkage. In the previous case, we have shown that one was the Is, but here the entire current will be considered because the entire current I flowing through the conductor is enclosed by this Amperian path. That's why we have taken here Hs equals to I divided by 2 pi h. And the flux density is given by Ds equals to mu naught into I divided by 2 pi h. Next, for a small region of having the thickness dx, supposed to say region having the thickness dx and 1 meter length of the conductor, the flux is given by d lambda is equals to d phi x. Very interesting here, both the values, the flux linkage and the flux in between this region will be equal in value because the entire current is confined. So d phi x, d lambda is equals to dx into dx into 1, that is mu naught into I divided by 2 pi x into dx. So the total flux linkage of the conductor due to total flux linkage of the conductor due to the flux between P and Q written as lambda pq equals to integration t1 to t2 mu naught I divided by 2 pi x into dx, that will give us mu naught I divided by 2 pi ln d2 divided by d1, mu naught I divided by 2 pi ln d2 divided by 2,1. And inductance between two external points of the conductor is as L external equals to lambda pq divided by I. That one is equal to mu naught divided by 2 pi ln d2 by d1. Just by putting here value of mu naught 4 pi into 10 to the power minus 7. Just by putting here value of mu naught 4 pi into 10 to the power minus 7. The expression is coming as 2 into 10 to the power minus 7 ln d2 by d1. Previous one was 0.5 into 10 to the power minus 7, but here the expression L external is coming as 2 into 10 to the power minus 7 ln d2 by d1. Now we are coming to the inductance of single phase two-well line. We are coming to the expression for single phase two-well line. So for single phase two-well line, now we have to consider both the conductors. We have to consider here both the conductors. Supposed to say one conductor having the radius R1, and there is another conductor having the radius R2. This conductor is carrying current plus I. And this conductor is carrying current minus I. The distance between the centers of two conductors is denoted by, suppose to say, capital D. There are internal fluxes also for both the conductors as well as the external fluxes also. So for the conductor 1, first one we are considering here the conductor 1, L1 external equals to 2 into 10 to the power minus 7 ln d by R1. How it's coming here? Just we are considering here the flux produced by the conductor, the flux produced by the current flowing through this conductor, conductor 1, with at a distance d, at a distance less than d minus R1, at a distance less than d minus R1, there are actually two considerations. One is, if we are considering the conductor 1, one is d minus R1, another one is d plus R1. What is happening? Let's see here. For d minus R1, this one is d, and this one is not d minus R1, it will be actually d minus R2 for if we are considering conductor 2. D minus R2, and this one is d plus R2. And you see here for the fluxes produced by the current flowing through this conductor at a distance less than d minus R2, at a distance less than d minus R2, links with the current plus I. And if the fluxes produced by the current flowing through this conductor at a distance greater than equal to at a distance greater than equal to D plus R2 will link with net zero current. Because both the conductors are carrying equal but opposite current. Because both of the conductors are carrying current equal but in opposite direction. And here we can take here that if D is much greater compared to the radius R1 or R2, then it can be approximated as D minus R2 as here D. Here also D plus R2 can be approximated as D. That means here the current, here the flux produced by the current flowing through this conductor will link with the, at a distance in between D minus R2 to D plus R2 will link with the current from 0 to I. Link with the current from 0 to I. So for simplicity, we can assume that here beyond the center of the conductor, the flux is produced by the current flowing this conductor will link with zero current. And that's why the approximation can be written as L1 external equals to 2 into 10 to the power minus 7 ln D by R1. In the previous expression, we have taken there D2 by D1. Here D2 is replaced by capital D and D1 is replaced by R1. D1 is replaced by R1. Next, total inductance of the conductor 1 now. The total inductance of the conductor 1 have the two parts. One is the total inductance of the conductor is having two parts. One is the internal part, another one is the external part. Internal part already we have derived it, that is 0.5 into 10 to the power minus 7, and another part is 2 into 10 to the power minus 7 ln D by R1. That one can be simplified further as 2 into 10 to the power minus 7 to 1 by 4 plus ln D by R1 equals to 2 into 10 to the power minus 7 ln E to the power 1 by 4 into ln D by R1, and further it can be expressed as 2 into 10 to the power minus 7 ln D by R1 into e to the power minus 1 by 4. 0.4605 log D by R1 dash. 0.4605 log D by R1 dash. Where R1 dash is nothing but R1 into e to the power minus 1 by 4, which is smaller in value compared to the actual radius of the conductor, that is 0.7788 R1, 0.7788 times of R1. These radius R1 dash, which one is smaller compared to the actual radius of the conductor, is called the fictitious radius of the conductor. This R1 dash is called the fictitious radius of conductor. And what's the physical significance of this fictitious radius? That is, there is nothing but the skin effect. Due to skin effect, we know that the effective radius of the conductor is decreased. That's why here this radius is called the fictitious radius of the conductor, which one is smaller compared to the actual radius of the conductor. Similarly, inductance of conductor 2 can be written as L2 equals to 0.4605 log E by R2 dash. In the same way, the inductance for conductor 2 can be written as summation of the internal inductance and the external inductance. So total inductance of the circuit can be written as L1 plus L2. Total inductance of the circuit is nothing but the summation of the inductance of both the conductors incoming and outgoing, that is 0.921 into log D by R1 dash root over D by root over R1 dash into R2 dash. So total inductance of the circuit, we have written here L equals to 0.921 into log D by R dash. Now, again consider the expression for the inductance for conductor 1 and as well as the conductor 2. Here L equals to 0.4605 log D by R dash. If we can assume that here, if the two conductors are identical in nature or having the equal radius, then we can write it as R1 dash equals to R2 dash equals to R, supposed to say R dash, then we can write this expression as L1 equals to 0.4605 log D by R dash has been taken as the summation of log 1 by R dash plus log D by 1. In the same way, the conductor for conductor 2 is written as 0.4605 log 1 by R dash plus log D by 1. So inductance per phase per kilometer length of the line. Inductance per phase per kilometer length of the line and written as L equals to 0.4605 log 1 by R dash plus log D by 1. Just see here, there is one self part, another one is a mutual part. D is coming for the effect of mutual inductance. And from this expression, the concept self and mutual inductances have been arrived. So flux linkages can be written as again here, considering here the two conductors there are the two conductors carrying current I1, another one is carrying current I2. The self-inductance is L1 here the self-inductance is L2. And the mutual inductance is written as M12 equals to M21. That is, mutual inductance can be written in between the two inductance can be written as M12, that one will be equals to M21. Because that is the mutual flux linkage between these two conductors. As well as that is the self fluxes also. So here this expression can be written as the flux linkage for conductor 1, lambda 1 equals to L11 I1 and plus M12 I2, lambda 1 for conductor 1, L11 I1 plus due to the current flowing through this conductor M12 into I2. The flux linkage with the conductor, with the current flowing through this conductor, that one is a mutual, M12 I2. In the same way, the lambda 2, for the, if we are considering the conductor 2, then lambda 2, total flux linkage of this conductor can be written as M21 due to current flowing through this conductor I1, M21 I1 plus L22 due to current flowing through this conductor, that is L22 into I2. Actually, the self-inductances will be L11 and that one will be L22. Self L11, L22 and the mutual is M12, M21. Now, we are assuming here the net current is 0, that is the two conductors are carrying the equal current but in opposite direction. Okay, that's why I1 plus I2 equals to 0. So this expression can be written as if both the conductors are carrying current equal in magnitude but in opposite direction, then we can write this expression as I1 plus I2 equals to 0. And then this expression can be written as lambda 1 equals to L11 plus M12 into I1. And lambda 2 equals to minus M21 plus L22 into I2. And here L1, that is the total inductance. L1, that is the total inductance having the self part, another one is the mutual part. L1 equals to L11 minus M21 and L2 equals to minus M21 plus M22. And here we have already derived this expression. L11 equals to L22 equals to 0.4605 log 1 by R dash. Log 1 by R dash. And what's a mutual? For mutual inductance, M12 equals to M21 equals to 0.4605 log 1 by D. Log 1 by D. For self part, it will be log 1 by R dash. For mutual part, it will be log 1 by D. Multiplied with, both of these are multiplied with 0.4605. Now suppose to say there are n number of parallel conductors carrying current I1, I2, IA, such that the phasor sum of this currents are 0. Then what will be the general expression for self and mutual inductance? The generalized formula for flux linkage, the generalized expression for the flux linkage can be written as lambda equals to LII, that is the self part, summation plus summation of the mutual inductances, that is M or mutual flux linkages, that is the Mij. We have to take the limit from J equals to 1 to N, but J not equals to I. That means while we are considering the ith conductor, then for self part only we have to consider here the current flowing through this conductor, ith conductor. But for having the mutual inductance, we have to consider the current flowing through other conductor except ith conductor. This one is the generalized expression, this one is the self part, and this one is the mutual part. And again we can express this expression as lambda equals to 0.4605 to II log 1 by Ri dash, because LII can be represented as 0.4605 log 1 by Ri dash, and Mij can be written as summation J equals to 1 to N, J not equals to Ij log 1 by Dij, log 1 by Dij, where Ij is nothing but the Dij is nothing but the distance between the center of the conductor, ith conductor, and the jth conductor. This one is the generalized expression for the flux linkage of the ith conductor having n number of conductors. And this is all about today's session. Thank you.